I have started recording. Off
Okay. Hey guys, I'm Peter. Today I'll be talking about blue stragglers in a particular globular cluster called Omega Centauri. So Sohan kind of went over a lot of the basic stuff we did was the same. So I can skip through that quickly. So I'll go through the stellar evolution stuff, and then I'll talk about globular clusters and Omega Centauri in particular, and what I did, my analysis of it, and what it means for that cluster. So once again, we have these Hertzsprung-Russell diagrams and color magnitude diagrams, which we're going to be using again to look for blue stragglers. I'm specifically going to be looking at one globular cluster called Omega Centauri. And Omega Centauri is really weird as far as globular clusters go. It's the most massive out of all of them by an order of magnitude. There's decent evidence for a hypothesis that it's actually not like the other ones, and it's the core of a captured dwarf galaxy. There's also some evidence that it has an intermediate mass black hole in the center. It's got a lot of X-ray emission, and important for this talk, it has three distinct main sequences. One filled with metal poor stars, one with stars that have kind of an intermediate amount of metals, and then one that has a high amount of metals. And when I say metals in astronomy, that means just everything heavier than hydrogen or helium. So carbon is a metal for some reason. So as far as blue stragglers go in Omega Centauri, it has a lot of those too. A study in 2006 found around 300 candidates, and those were just identified photometrically. So that study didn't remove any foreground or background stars, but they're still able to do some pretty good statistics. What they noticed specifically was that there were no head-on collision blue stragglers. They were all from binary stars merging together or triple systems merging together. And on top of that, there was no central spike in the amount of blue stragglers. Typically, we would expect that over time, binary systems within a certain radius of the center of a cluster would migrate inwards. So if we have all these blue stragglers that formed from binary stars, we would expect that they would be clumped in the center, but they're not. They're pretty evenly distributed, and they follow the same distribution as other stellar populations. So what that study looked at was just luminous blue stragglers. And Sohan mentioned this. You can kind of divide things into bright and faint blue stragglers. And a lot of the time, faint blue stragglers will have different origins. Sohan also mentioned 47 where we do see a strong central peak in the luminous blue stragglers, but the faint blue stragglers, there's none of that. So for Omega Centauri, the questions we want to ask are, do these faint blue stragglers have the same origins as the luminous blue stragglers in this cluster? And can that tell us anything about the history of this cluster in particular, or things about blue stragglers in general? So similar to Sohan, I used Gaia's second data release to pick out foreground and background stars and identify just purely members of the cluster. I cross-matched this with a really big catalog of photometry on globular clusters, and then just picked out blue stragglers by eye. So there's kind of some problems with the Gaia data in that it's missing some central regions of the cluster, and also the error on the proper motions is kind of high. So I made some cuts here. This graph is a graph of the positions of cluster members that I picked out. So you can see it's sparse in some places. I'm hoping to maybe go back and fix this once data release 3 comes out, maybe this year, pandemic permitting. So we'll see how that goes. But for right now, here's a color magnitude diagram that I generated. We can see pretty clearly the main sequence down there at the bottom. And I've outlined it in purple. And you can kind of see, if I overlay it, the three different subpopulations. So in blue there, that is the metal poor population. green is the metal-rich population, and red is, or green is the intermediate metal population, and red is the metal-rich population. So here's the selection box I picked for blue stragglers. You can see there's some stars in that box that I didn't select just because I thought they were a little too close to the main sequence turnoff or a little too close to the horizontal branch up there in the top left. We can fit an isochrone to this for a very low metallicity cluster that's only 2 gigayears old. So we can see that we can see the luminous blue stragglers seem to correspond to low metallicity. And we can also select down here this clump of other blue stragglers, faint blue stragglers. And you'll kind of see one thing that's different. Most of the time we talk about luminous and faint blue stragglers, they would all kind of be in the same selection box, and the faint ones would just be the lower half of the selection box, or maybe below a certain magnitude. It's kind of arbitrary how it's decided. But the reason I'm selecting these as faint blue stragglers and not just noise is because, one, they're clumped together. Two, because we have different main sequences here, I think that there could be different main sequence turnoffs hiding under here. And so we might have different populations of blue stragglers. And if we fit an isochrone to this population of blue stragglers, the thing that works is actually a high metallicity isochrone. So, do these faint blue stragglers in Omega Centauri come from this weird high metallicity subpopulation? One other thing about that subpopulation, there's a hypothesis which is sort of debated that it might have come from some other merger, either with the Milky Way or some other globular cluster. It's losing evidence in the literature right now, but we kind of want to look at this population and see where it came from. So that's kind of why we're looking at these faint blue stragglers. So anyways, one way to check for the metallicity of these stars is to look at an ultraviolet color magnitude diagram. So before, back here, you can see at the bottom, it's B minus V against V, which is visual magnitude. So we want to do U minus V, or ultraviolet minus blue, against blue magnitude. So if we look at that, we can see that there are some stars which have an ultraviolet excess, but a lot of them don't. So it would make sense, right, if these fainter stars had more metals and were dimmer because of that. But it's sort of unclear if that's actually the case. So what have we figured out? These different blue straggler populations in Omega Centauri might have different origins, but we need to do more work to kind of dig into the separate populations within the faint blue stragglers. And to identify more members, we kind of need to wait for Gaia's next data release. But possible next steps, aside from just waiting for that, one thing I was working on but didn't quite get done for this was looking at ultraviolet images from SWIFT, the gamma ray telescope, and also Hubble. And I'd also like to maybe do some of my own stellar evolution modeling and make my own isochrones and stuff to see if I can reproduce this system. Are there any questions?